PSS, Postal Service over Swarm. This is the right acronym, isn't it? Huh? Okay, let's have the other ones, Vic, because I didn't memorize them. Well, it suffices, yeah? So basically, semi-dark messaging, providing end-to-end encrypted messaging, using the swarm Kademlia routing, and ultimately with the whisper encryption. So, currently the way to send messages in the Ethereum code base is either through the dev P2P connections that Felix was talking about earlier, or Vlad's project, the Whisper, which basically tells every node to pass on the message to everybody, and without the recipient address. And every node that gets the message try to decrypt it, and if they can decrypt it, it's for them. If they can't, it's not for them. That's basically summarizes it, right? Now, this is very dark and very good for very paranoid people, but if you're slightly less paranoid, then it could be advantageous to speed it a little bit up, because obviously a solution like this is rather expensive, can be a little bit delay. Therefore, if we introduce a to address into this, we could actually utilize the routing algorithm, the routing capabilities in Swarm to direct the messages. So this is what PSS does. So basically, it's dev P2P, but you don't have to be directly connected to the other node with a TCP connection to send or exchange the messages. So, I will describe how currently the data structure of a PSS message is set up. It's a good starting point, isn't it? So first, we have on top the PSS message structure. This currently only contains, and will also only contain, a to field. The to field is the swarm address of the node you want to send to. Then there is a payload, which now is an arbitrary envelope structure. But in the end, the plan is to utilize the whisper encrypted envelope structure for this, so it's impenetrable. Now, this structure here is actually past dev P2P. So you want to send to some node you're not directed to, so you send this message to the next node with dev P2P. It looks, is it for me? No. If it's not, then it passes it on, and so forth. And the code, the way this is done now is the node gets the message. It takes, if the to field doesn't exactly match, it calls the Kademlia iterator and says, give me all the peers that are closest to this address in order of proximity. And the proximity order is, as aforementioned, the notion of closeness in the Kademlia routing. If there is a sane network and we're connected, we'll get at least one node that we can pass on the message to. And it passes on like this. And without being a mathematician at all, but the idea is that it will be a as the Kademlia as such, a logarithmic scale to the steps from one node to another to pass on the message. Now, there is also a cache guard in place currently. When a node gets a message, it stores a digest of this message on Swarm. It uses the hash it gets from this digest, adds it to a cache table, so that within a certain time span, it gets the identical same message, that it's the same recipient and the same hash, it drops it. Now, this is probably a very primitive and naive way of trying to prevent any brute forcing, but it's at least the start of doing something. But what it also provides, and what is more important, is that it prevents nodes from forwarding the messages backwards, in the sense that if the node sends to another node, which only has the originating node or the forwarding node in its Kademlia table, it will try to send it back. And that's not what we want. So then it drops the message. Now, this encapsulates the payload. The envelope contains the sender address. Now remember, this will be encrypted, so nobody on the way will be able to see this until it reaches its destination and it's decryptable, which is, of course, the Swarm overlay address of the sender. It contains a topic, and it contains, well, again, the inflation of the term payload, but it's payload again, which is the actual message we're trying to transmit. Now, for the payload, this can be absolutely anything at all. Any arbitrary byte slice that you want to include. It is totally unopinionated. As for the topic is a notion of a certain, so a theme for which messages belong together. And it could be, let's say, a chat room. It could be a social media group. Or it can also be analogous to a protocol. And there is a convenience design in the current code base, or the current code of PSS, that makes it possible to act as if we're actually sending dev P2P protocol messages between nodes that are not directly connected as well. Exactly. So inside the dev P2P code base, there is the central object that handles the in and out is called the message read writer. It's an interface in the Go Ethereum implementation. And what I've done in the PSS is to kind of hijack this message read writer. Now, usually it's on each side of a connection, but when the PSS gets a message in, it's able to inject the message into this structure so that it appears on the read side of it. For this, we have an object that's called a protocol message, which is sort of a distilled or a static version of the P2P MISC object in the code, which is basically, so the P2P MISC contains code for the message, it contains the buffer for reading the payload, and the size, and this convenience object that is in the code, it is an unbuffered version, so it's a serialized byte slice of the content. So, back to the notion of topics. One topic can be, let's say, a protocol, for example, or any kind of group of themed content. Now, the way this works is that the PSS has a dispatcher. You register handlers for specific messages. So you register handlers per topic in PSS. And you can have many handlers for one topic registered, which means that when the message comes in, several different functions can be invoked on the same message. This is practical, for example, in the implementation of the RPC API. We have the PSS RPC API, which basically does this. It registers a handler that gets all the messages to a certain topic, and then it passes these messages on to whoever's listening on the WebSocket. So we have a WebSocket subscription service on the RPC. You can connect through WebSockets and get all the messages that are sent to a certain topic, which means that any external code can also handle and use the PSS node as a proxy. Furthermore, there is implemented also something called the PSS client. The PSS client is a convenience abstraction for the API, so that you don't have to actually connect directly to the WebSocket yourself and handle that chatter, but instead it provides a way of mounting the protocol code on top of the WebSocket communication layer. So basically you're using PSS as you would do a totally normal protocol, and also separated from the node that is running the PSS. So basically you can implement software totally separated from the PSS code base, only using WebSockets with this as a convenience filter or a convenience method. Right. I've documented all of the PSS core functionality, the API, and the PSS client as the current status is. It's all on GitHub. I wanted also to show you, but I will show later on when I hopefully prepare better. For Saturday, there is going to be a tutorial that shows hands-on how to actually implement something using PSS with the current code base. And there I will also show I've written a small chat client that kind of mimics the I don't know if you know this old talk application from the BSD systems where you have the terminal window and you split it in two, and one writes on the one side and one writes on the other. So there is a proof of concept application that I've written which actually uses this layer here, PSS client, and exemplifies how you can write software with this at this current version. And yes, so I will show that on Saturday. But before that, if anybody wants to come and chat with me on using this, or curious about how it works, I'm happy to show.